The function f of x equals e to the x, centered at base point x equals 0, can be represented by the infinite Taylor power series, the summation as n goes from 0 to infinity of x to the n over n factorial. And this is the formula. How do you get this formula and why? To make a Taylor series, first you must make the Taylor polynomial. P sub n of x equals f of c over 0 factorial plus f prime of c times x minus c over 1 factorial plus the second derivative at c times x minus c squared over 2 factorial plus the third derivative at c times x minus c to the third over 3 factorial, all the way up to the nth derivative of f at c times x minus c to the n over n factorial. Why? The polynomial is a good way to get an algebraic approximation for a transcendental function, which means a non-algebraic function like trigonometric, inverse trigonometric, base e exponential, and natural logarithmic functions. As n increases, the polynomial above becomes a series if n continues to approach infinity. Here's the series as the summation as n goes from 0 to infinity of the nth derivative of f at c times x minus c to the n over n factorial. The graph of the polynomial becomes closer to the graph of f of x near the c base point. Now looking at f of x equals e to the x, centered at c equals 0 base point, here's your original function, e to the x, evaluated at 0 is just 1. The derivative of e to the x is e to the x dx, and the derivative of x is just 1, so it's e to the x. Derivative of e to the x is always e to the x, so all of the derivatives will all be e to the x. And evaluating at 0 will all give you 1, all the way down through. To form the first degree polynomial approximation, p sub 1 of x equals f of c over 0 factorial plus the first derivative at c times x minus c over 1 factorial. For e to the x at c equals 0, e to the 0 over 1 is just 1. E to the 0 times x minus 0 over 1 is just a 1x over 1, which is just x. And to the right, here are the tables. First is a table of e to the x, and then the linear approximation 1 plus x. And notice here's your linear approximation, and they meet at the x equals 0 value, the c equals 0 value, at 1. But that's the only point where they line up. To form the second degree polynomial approximation, we will add a third term, the second derivative at c times x minus c squared over 2 factorial, which will be 1 times x squared over 2. Why are we adding an additional term? Let's look at the graph. Okay. In red is the e to the x graph, and in blue is the quadratic, the parabola. Okay. You can see that the red and the blue lines are closer together than the linear approximation was, but there still is some distance between the two graphs. How far away is the polynomial graph from the real graph of f of x? The remainder is the distance between the function and the polynomial. The remainder, r sub n of x, is equal to the function minus the polynomial. Let's add that remainder to the polynomial to make them equal, just changing this formula around. F of x is equal to the polynomial plus the remainder. The remainder can be found using the Lagrange form of the remainder from Taylor's theorem. R sub n of x equals the n plus 1th derivative of f at z, some z value between x and c, times x minus c to the n plus 1 over n plus 1 factorial. This is the next term of the polynomial that we are going to add, which may be a positive or negative value. Each polynomial of n degree approximation can have an additional remainder added to it to make a new polynomial approximation of one higher degree that is more accurate. The third degree polynomial approximation is p sub 3 of x, where the first three terms, or four terms, 1, 2, 3, first three terms are the same as previously, and now we're adding the third derivative of f times x minus c to the third over 3 factorial, which evaluated for e to the x at c equals 0 is going to be e of 0, which is 1, times x minus 0 cubed over 3 factorial gives you 6. 3 times 2 times 1. So there's your fourth term. Let's look at the graph, see if it's any closer. Okay, so now you've got an odd function. Before we had the quadratic parabola was an even function, so now it's coming down from the bottom and coming up, and they are much closer together than they were before. And we've picked up, so we're going to pick up more points as we go, and they're going to, as we add more and more terms, we'll have more points that follow the red line. Remember, the red line is the e to the x graph. Let's compare the points. Negative 1 for e to the x gives you 0.3679, and here negative 1 is 0.333. Here positive 1 is 2.7183, positive 1 is 2.6667. Let's keep going and look at the fourth degree polynomial. Here's its approximation. We're going to add the fourth derivative at c times x minus c to the fourth over 4 factorial. 4 times 3 times 2 times 1 gives you 24. E to the 0 is 1. That's going to be 1x to the fourth. Here's your 1, 2, 3, 4, fifth term. Okay, let's look at the graph. Okay, now we're getting even closer to our original e to the x graph. Okay, and now we have an even graph. As we toggle back and forth between odd and even, this is going to flip up and down. Okay, let's look at our negative 1, 0.3679, positive 1, 0.375, much closer. Positive 1, 2.7183, positive 1 here, 2.7083, very close. Let's look at the fifth degree approximation. Now we're going to add the fifth derivative of f at c times x minus c to the fifth over 5 factorial, which is going to give us 1x to the fifth over 5 times 4 times 3 times 2 times 1, 120. And let's look at its graph. See, now we have an odd function, okay, but the points, we have more and more points that are lining up with the original e to the x graph. We've picked up a third point over here on the negative side. It's very close. And you can kind of see from the table. Let's look at even 2 here. The value of 2 e to the x is 7.3891. Value of 2 here is 7.2667. Okay. Let's see. Negative 1 is 0.3679. Negative 1 here is 0.3667. Okay. Let's go to the sixth degree approximation. We're going to add the sixth derivative of f at c times x minus c to the 6 over 6 factorial is going to give us 6 factorial is 720. So we have x to the 6 over 720. And now we have an even graph. And let's see, so it's not really approaching the negative side very accurately right now, but the positive side is very close. And you can compare the tables. See, positive 2 is 7.3891. Positive 2 here is 7.3556. So it's getting a little bit closer even around the zero values. X to the seventh now. Looking at its graph is x to the seventh over 5040. And you can see now we've got an odd function, but the graphs are matching up very nicely on this side. And now this one is on the down below. How about x if we add an x to the eighth term? Okay, so this is your 8th degree polynomial approximation, and you can compare the original values. At 3 it's 20.0855, here it's 20.0092. Negative 2 is 0.1353, and here it's 0.1365. And you've got not a great, not a good comparison on the negative side, but a very good one on the positive side. And as these remainders keep getting added on, this is going to toggle back and forth between being above and below, and we will keep picking up more and more points, and eventually these graphs will match until we will have the equation over here that we started with, and that will be our formula for the representation for f of x equals e to the x. Thank you.